we still, that should be that for stability, but I still have to obsess about it a little bit longer because I'm discovering that everybody is confused about a quantity and its logarithm, or everybody is confused about multiplier, I'll define it in a second, and its properly defined logarithm, which is called exponent. And I don't know why is it this way, but that's the fact, so I'll spend another lecture just to make sure that you distinguish logarithms. Allow me to, torture you with cycle stability for a while. And lots of it's tedious because, I feel I have to say it very clearly so later on we don't be confused. There are no confusions. So this is a whole chapter of stuff like that. And I have to explain the motivation for it. In almost any physical problem, and you know this very well from quantum mechanics and from special and general relativity and particle physics. Almost every problem we like to use some general symmetry principles, etc., to write what we believe is fundamental equations of motions. So basically we set up some kind of Eulerian field, or a Newtonian way of thinking. And then we are asked to make predictions. Now, in some parts of physics, what people do is they immediately go and do another problem, because once they've written an equation, that's for engineers. So they go to the Planck length, or someplace where nobody can bug them because nobody cares. But if you're doing, cardiac or fluid dynamics, other people actually have to see what the consequences of the theory are, if this is really a theory. So you need a Lagrangian picture. You actually need to explain what the spaghetti are in the state space. There is more to it than just writing the equations. And sooner or later, and in general relativity and nonlinear dynamics, rather soon, you realize there's an enormous amount of arbitrariness how these fundamental equations were written. So that's called principle of general covariance, etc. So, whatever law of nature I write in any coordinates, I'm allowed to do anything to those coordinates unless I do something criminal, like I slice space and make it discontinuous. But as long as I have a continuous coordinate transformation and describe what I'm doing, all of these things should be equivalent. So actually these problems that look totally silly to you because you know that potential is 1 over r in spherical coordinates, and that Rossler wrote 3 equations and you ran them on computer. The real issue is, if I predict something, is the prediction invariant? So in particle physics, what I predict charge and mass of a particle. So things I can measure. It doesn't matter how I do it. Russians use some notations, and Chinese, Japanese, etc., other notation, and the world is connected. So regrettably, by now, everybody is using pretty much the same notation. But that is not the content of the theory. So you have some enormous world of possible description of the system, and you are supposed to give predictions. And those predictions have to be invariant, meaning that no matter who does it, how does it, we all agree that this is the same thing. The invariant are the coordinate changes, the invariant are your definition of the time, etc. And that's why we will get in these cycles, which is a short word for periodic orbit. Cycle is easy to say, and for some of us who like bicycling, it comes very naturally. But there are lots of things in mathematics that call cycle. A periodic orbit, everybody agrees what it is. It's a set of points which are revisited in time periodically. There is no discussion. And what are the invariant sets? Now, our dynamics is still beginning of 20th century, so the time is Newtonian, space is absolute, also Newtonian. And invariant sets are things that don't change in time. So, if you want to emphasize it, they could be called time invariant sets. If you have some other symmetries like translation, rotations, etc., then could be group invariant. But this is the simplest, well, not the simplest, but this is the first natural notion of invariance. So these are the subsets of my space state that don't change in time. So they say equilibrium, same in state space, and every place there is a law that tells me how I move. At this point it happens to be 0. This velocity is 0, so I don't move. Then the next object, so this is dimension 0. Next object, which is very natural because that's how science got started, was periodic orbits. So it's a curve of one dimension embedded in million, doesn't matter what your state space is. And it has a property that every point on it, so if you label it, you can label it by time. And if you're Kim, you can call it x of s, or s is a general parameter that you put there. Doesn't matter. And it'll have the property that if you insist on using a time t later, you're back. That's true for every point. And velocity fields should be non-zero every place, because if it's 0, that's called something else. That's called a heteroclinic connection. That's not a periodic orbit. Periodic orbit is where everybody marches at different velocity at different times. But you can never catch up with the person in front of you or overtake them, because that would be violation of determinism. You just couldn't do this. So everybody marches around. So as an army, they're an invariant army under time. And then the truth is that there is an amazing amount of mathematics. One of them actually got Millennium Prize and Fields Medal. Neither one of them collected, by Perelman. But there's an amazing amount of mathematics that says, in general, there could be other invariant sets. So there could be bagels, or there could be genus n things, or there could be God knows what. And we're in very high dimensional spaces, so there's lots of candidates for invariant sets. And the truth is that we really don't, today we don't really know much, at least dynamicists I know, maybe some very good mathematicians know much more, but we don't know much more than tori as invariant sets, and they're very important. They have to do with stability of the solar system, etc. So they're extensively studied. But that's what we have to do. So what can we say about equilibria from what we know so far? Equilibrium. Equilibrium is something that has a property that x, equilibrium Q, let's give it a name. We usually label solutions by some kind of label. So Q has a property that when I look at evolution time t of Q, it just stays where I am for all times. So it looks like there's nothing interesting, but however, if I look at the neighborhood of Q, something will happen, because neighboring trajectory, even though I'm not moving, they have non-zero velocity fields, because generically I should say the equilibria are isolated unless there is a symmetry principle that forces them to be in families. But usually you have some general function, you're computing 0 of it, that's the map forward in time, minus initial point, and generically they tend to be isolated zeros. So when I look at the neighborhood, The law is very simple. We already did this because if I look at the difference of x minus the initial point xq, so I look at this as a function of time. At time 0, I have a thing. And now, because this is equilibrium, the matrix, which is a gradient of the velocity field, because I am evaluated at this point, A is also just function of the point and constant out of, it's constant. Do you agree with me? The matrix of velocity, okay. But we already did the actual thing for constant matrices. So we know that this grows like E to this constant matrix AQ. I'll just label it because it's a constant matrix. And it's exponential and changes with time. So, you know, the Jacobian is known the moment I know the matrix because there's nothing about time ordering. It's all simple. It says it has very simple dynamics. The neighboring points are just being pushed out or squeezed or rotated exponentially by this matrix. And you know, you can see that the time t is bogus because it doesn't, the only thing you really should know is the eigenvalues of that object. And that's why in quantum mechanics, this is called Hamiltonian operator. That's why I compute eigenvalues of the Hamiltonian, and that tells you what happens to the vector in time. I mean, so Hamiltonian is an exponent, and in quantum mechanics, this object here is called unitary evolution operator. But it's e to the integrated Hamiltonian. So we only have to know what this is. And for that, we know that if you have any matrix, it will have eigenvalues, lambda, I. You'll have, in general, d of them, and they can be real or complex pairs, because this is a real matrix. And we'll have eigenvectors. And now eigenvectors give us a very natural basis, because, you know, if you think of this as a Taylor series, so e to this matrix is the sum of powers of that matrix, acting on the eigenvector, this will give me this thing back. So I have that you know, E, this evolution operator TA acting on A, I mean acting with A exponentially, acting on an eigenvector in the I direction, will simply return back e to the t lambda eigenvalue in that direction. So the moment I find the spectrum of this operator, which is in the exponent, I actually also know what the Jacobian does, the linear flow is, which is, you know, exponentiates. And all it does is eigenvectors are the same for this object and that object. And along each eigenvector, if it's a real eigenvector, that it either expands or shrinks depending on the sign of lambda. And if this is complex number, then I have to take pairs and think a little bit about it. So everybody is okay with this? So that solves the problem of the simplest invariant of equilibrium. We know what linear neighborhoods do. Now, you know, parenthetically, to anybody in class or outside of class, when we derive trace formulas, they'll be derived for periodic orbits. And for some reason, I don't have intelligent trace formula for this simpler object. So if you have a good idea, let me know. Erudite remark, you can ignore it for now. So that's the simplest one. What about the next object of interest? That would be a periodic orbit. So what is the stability of periodic orbits? If you remember, when I discussed general Jacobian, so when I discussed Jacobian, that where you start at x0, you end up at xt, I observed that if I look at velocity vector at x0, then the velocity vector, which is tangent to the curve, to the trajectory at last point at x of t, is actually given by the Jacobian. I mean, it's a hokey thing because we had it already, so it's not like we are computing velocity field. But we observed that if you think in the way of, American general on the Minuteman missile, every time, wherever I am, I'm pointing forward with my missiles. So I'm always seeing the tangent locally. And once you have gone some time later, it turns out that Jacobian maps this vector into that vector. So in general, this means nothing because these are different vectors, so this is not an eigenvalue condition on the, this is not eigenvalue equation. However, for periodic orbit, what happens is we go, and we come back, and we find out that velocity vector at the end at time t, if this was x0, is the same velocity vector as at the original time, because I come back to the same point, and velocity vectors only depend on where I'm state space. It's autonomous, they don't vary in time. But I have this equation that says the guy at the final time, which happens to be the one at initial time, is just Jacobian going one period. In other words, for the periodic orbit, always have one eigenvalue I already know. So I have eigenvalue 1 with eigenvector v of x. Now, when you think of it, this is totally obvious, because if I take two nearby points on the trajectory, after one period, they'll be exactly the same distance. So they'll spread, come closer, but they never overtake each other, go around. So here they'll go like that, this interval, and here they might slow down. And when they come back, they'll be exactly the same distance. So along the flow, for a periodic orbit, not for a general trajectory, only for periodic orbit, there is no shearing at all. Intervals have exactly the same size. And these eigenvalues are telling you what the shearing is. So there is always eigenvalue 1 for periodic orbit. Now this is not a property of any finite trajectory which is non-recurrent. Kimberly, yes?
I have a question.
Kimberly has a question.
Of course I have a question.
Of course I have a question.
You said something about them being separate the same distance, something like distance. But distance is relative to a metric or something you have to be able to...
In any metric.
Yeah, I mean, so it seems like we should...
Same distance in any metric.
Notion of, I mean, are we saying we compute like a geodesic and then we use it to measure relative distances, or
So if we measure the distance in any, if the metric means that the size of this interval here, delta x, which is approximately, well, just delta x. Okay, so as a vector, this is a number, some magnitude, some number of v divided by v magnitude. So if I take a unit vector here as a tangent vector, whenever I have velocity, I can define a unit vector, right? So you give me my vector field, and I'm allowed to add and multiply by scalars. So the magnitude of this is a number that I multiply this unit vector. Now, I'm cheating because to define the length of unit vector, I'm using norm in here. So this thing is, squared. It's delta x I g I j delta xj, where that's the metric. Euclidean metric is just 1, 1, 1, but in general dynamical system, there's absolutely no reason to use Euclidean metric. You have to really think about what notion of distance mean in general. Though, in Newtonian space, it's okay, but not in general. So, so now what happens is this metric in general depends on where I am, but I'm not allowing time dependence of the state space itself, including the way I triangulated and measured the distances. So this will not be time dependent, just space dependent. Then the argument holds because when you come back, you're evaluating the metric at the same point. So no matter what distance you're using, it's the same distance. Are you satisfied?
No, more or less. I mean,
more or less.
More or less. But if we're going to be talking about
let's take a vote.
Objects.
Let's make this Egypt and we take a vote. Everybody votes except Kimberly. No, it's okay.
If we're going to be talking about invariant objects, it seems like we should think about things in a coordinate-free sort of frame, independent of parameterization, possible, those sorts of things.
Yeah.
I guess that's it.
I actually, you're way ahead of everybody, including me, but I actually very much agree with you. No, seriously, because this J that we define is coordinate free because the J if you look at dxi, dxj, and you do any coordinate transformation, so you go to new coordinates yi, which is some nonlinear but invertible and smooth differentiable, etc. thing of x's. So if I go to new coordinate system, so I was in M, but now, German state space, but now I'm going to Japanese state space, and it's described by unique mapping of 1 to 1. Then when you work this out, and we'll do this later in this chapter, but probably not later in this lecture, which I guess I have to split chapter in two, we will prove that Jacobian itself is invariant under all smooth coordinate transformations, so on the whole general covariance group. And the idea is very intuitive. Jacobian is comparing infinitesimal neighborhoods when they come back for periodic orbit, by the way. And as I apply my stretching and squashing on periodic point, I stretch and squash, both x upstairs and downstairs by the same h function, and they cancel in linear order. They don't cancel in higher orders, and that's why it's very hard to define nonlinearity. The parabola is very hard to define in these terms. You immediately get into connections and blah, blah, blah. But the linear order is fine. So your question is extremely good. Okay, so everybody